Hello student, I am Arnab Das. Today we discuss about the distance property of a linear block code. Having distance, first of all, it will be common there for a property of a linear block code. Having distance of any two code vector is defined as the number of bits in which they differ. For this reason, we just consider the two code word as I say this is C1 and the C2, where C1 is defined as a 11011010 and C2 is defined as a 10111100. These two are the code word and we are interested to identify what is the Hamming distance between this C1 and C2. Hamming distance, it is defined as a form of D within a bracket C1 comma of C2. That means D is defined for the Hamming distance and C1 C2 is the code word for we are interested to identify the Hamming distance. So if you check individually the column 1 from the MSB side or the LSB side, if you consider from the MSB side, that time for the C1 is 1 and second for the C2 is 1. So for the MSB position then no alter is occurred. Now for the second MSB bit it will be value for the C1 is 1, C2 is 0. So here one data is changed on there. Now for the third one position, this is the 0 and this is the 1 for the C2. So here also the data is alter or change, that is the differ. Now for the fourth position, both are the 1, C1 and C2 both are the 1 on there. This is both are the 1 on there. So what happened here, no differ will be changed on there. So in such way, if you count on there, number of total variation is 4. And for this reason Hamming distance for the C1 and C2 is 4 on there. So one by one check process you can able to identify the value for the Hamming distance. But in the another way you can also got this one, that is you have to do the XOR operation between C1 C2. For the C1 C2 if you build the XOR operation, that time the result will become as a 0 11 0 11 0, and then you have to count the how many number of 1 is there for the resultant. The number of 1 is there total for the resultant is 1 1 in this position and another 1 1 is this position. That means total 4 1 is present on there. So the Hamming distance for the C1 and C2 will be 4 on there. So this is the another way by which you can able to identify how many or what is the value for the Hamming distance for this two code. So first one is that you have to identify that how they are differ, or second way you can identify by using the XOR operation, or this is also defined as a mod 2 addition between these two codes, and the resultant position how many number of 1 is present, you just count that one, it will be defined the value of the Hamming distance on there. Now for the Hamming weight of a code word is defined as the number of non-zero element in a vector. Number of non-zero element in the vector, that means you have to count how many number of 1 is there. For example, Hamming weight for 11110, for this one how many number of 1 is there for this code. For this code if you want to identify how many number of 1 is there, so you just count the 1, so their total 1 is 5, and for this reason 5 is define the Hamming weight for the particular code of this one. If you consider for this one, that is the 10111100, how many number of 1 is there, the total number of 1 is 4. So 4 is the Hamming distance for this code. Okay, so you have to count only for the individual one code the how many number of 1 is there. So on that way you can able to identify for that particular code what is the Hamming weight. Hamming distance of any two code word, that is C1 and C2, is the Hamming weight of the vector from by perform the binary addition of C1 and C2. So we already talked about that one. uh, we already told you that this is the process by which you can able to identify the Hamming weight. That is, the D is defined the Hamming distance, and HW is defined the weight for that resultant value of C1 and XOR of C2. That means you have to initially do the operation of C1 XOR of C2, or this is the mod 2 addition, and the resultant value you have to count the Hamming weight, that is the HW. That will be should be the value of the Hamming distance for the C1 and C2. Now for the Hamming distance, for the minimum distance, for the minimum distance, which is also defined as a D min, this is defined the smallest Hamming distance between any two code word in the code. That means if you consider a 3-bit message, that is k is equal to, in there is a 3. So how many number of tuple will be there? 3 tuple will be there. That means 2 to the power of 3 number of masses will be there. That means this is equal to 8. For the 8 masses, then number of code word will be also 8. So individually, if you consider for the pairing for this 8 number of masses, there which one will be the minimum, or which one is the minimum Hamming distance, it will be defined the D min. So for this reason, it is defined as name of any two code words in the code, that will be defined the minimum distance. So in here, D min is defined as the minimum of C of I, comma of j. That is, D is defined the Hamming distance for the two code word, that is the Ci and the Cj, and should be remember that I not equal to j. Any kind of value can be chosen there, ij. That means for the 3 bits value, the total number of message, sorry, code word will be the 8. So here I or j, this one can be value of 1 2 3 0, from starting 1 2 3 4 up to j, whatever, up to 7. So whatever it can be, but they not equal each other. That means this one c1 and j not will be equal to the equal or same value. So if you consider this one condition, that is the Hamming distance, then the minimum one Hamming distance will be defined the D min, that is the minimum distance for that particular code. There's some theorem or conclusion can be make on there. You just recall for your further requirement. That is the theorem 17.1. Here 17 is specified for the class number of 17, and this is the theorem number 1. The minimum distance of a linear block code is equal to the minimum weight of a non-zero code vector. So it can be easy for understand also. Again, I just told you that minimum distance of linear block code is equal to the minimum weight of a non-zero code vector. So if the number of 1 for a single code word is minimum, then that will be the maximum value, or maximum condition can be occur for differ. That means the minimum distance can be able to identify through that one. Okay, now the theorem 2 is that for every code vector weight L uh, in a LBC, there exists L column is H matrix whose sum is 0. Theorem number 3 is that an n comma of k LBC, LBC stands for linear block code with a minimum distance of d min, is capable of detecting d min minus of 1 bit error. That means if you able to identify d-min for an code, that time for that particular code, how many number of error can be detected on there. Again, I just repeating, detect, not correct. This is the detecting can be occurred. This will be d-min minus of 1. If anywhere d-min is given to you as a 4, so d-min minus of 1 is defined as a 3 because 4 minus of 1. So here 3 number of bit position, if any error is occurred, that time also it can be identified, yes, there an error is occurred. Okay, so d-min is the one of the most important parameter which is required to identify how many number of bit can be detected for there for any kind of error. And another one theorem is that an n minus of k LBC is capable of correcting up to d-min minus of 1 pi of 2 number of error bit of a minimum distance d-min. You should also conclude about for this one case that d-min minus of 1, this value, if it is not coming as the integer 1, let this is coming as the 2.5. So here 2 is defined the integer value and this is 0.5 is extra as a fractional value. So here 2 number of error can be correct if the value is coming for the d-min minus of 1 by of 2 as a form of 2.5. If anywhere the answer is coming as 1.5 or 1.25 whatever, so that time their maximum error can be correct is 1 on there. Okay, so here only the integer value you have to consider on there. So by using an example, I think it will be easy for understand. Also the question is given that a generator matrix for an LBC is given as such. G is defined, recall your memory, G is defined the generator matrix. Okay, so from here initially have to find what will be the value for the n and k. N is defined the code word length. So here how many number of uh, uh, bit is used to build and row. So their number of row is, if you consider for the first row, so number of bit to design the particular row is total 1 2 3 4 5 6 7 8. So n is 8 on there. Okay, this will be defined the how many number of bit is used for the code word, individual code word, and k is defined how many number of message bit is there, so that will be defined the how many number of row is there. So this is number of row is 1 2 3 4, so k will be 4 on there. So again I just repeat that to identify the value for the n, to identify for the value of the n for the G matrix, you have to count how many number of column is there, and for the k you have to identify how many number of row is there. So from there you can able to identify the code word is what. So the question is given to you for the formation of 8,4 LBC, that is the n is the 8 and 4 is defined for the k value. Now second question is that write the G in the systematic form. Systematic form means you have to write down as a form of ik is to of p or p is to of ik. Whatever you have to prefer, you can apply on there. This is the systematic form for the G. So in this case, we just consider or we just prefer here p ik, um, and for this reason there's some step we are following. This is the G is initially given to you, so if you arrange this one form, that time the result will become, and lastly one after one step if you follow, then lastly value for the G as a systematic form will become as such. This is the G as a systematic form. Why here this one is defined the this side, that is the right hand side, this one define the identity matrix. This is ik, that means k cross k matrix. K is there 4, so there 4 cross 4 the identity matrix will be required. And here this side is defined, that is the left hand side, this is defined the p on there, that is the this is parity matrix. Now from here, the third question is that for the question number 3, for the C it is given that find the all code, or already this kind of question you done on there. So what you have to do, you have to follow the formula, this one, that is the V is equal to U. U is defined the code, message code. So message is 4-bit, so number of variation will be total 2 to the power of 4, that means this is total 16, and it will be starting from the 000, then this is 001, then it will be 0010, in such way up to 1111. So it will be just multiply with the value of the g already which derive, that is the symmetric g, systematic g. So you just write down on here. If you uh, multiply between them, already I told you that what is the easiest way by which you can able to identify. That means in here you have to check for, if you consider first row for the v u, so here 000, so the result will become there for the first one will be as a 0, because I already told that where the 1 is present, only that particular row you have to consider and do the mod 2 operation or XOR operation, whatever you have to say in the better form. So first one, each and every uh, row position value for the v will become as a 0. Now if you consider for the second one row for the u, so what happened, this is 0001. So here which 3 row you have to absolute on there for the easiest way, that is the this one row absolute, this one row, and this one. So lastly the value will be come on there 1 1, this will be the value will be come on there for the code word of 000001. So code word will be 11010001. Check that, this is 11010001. So in this way you can ultimately got the individual message signal, what will be the code word on there. The d mean, if you count on there for the individual code word, for the first cases there no one is present, so here this one not you have to consider, this is not applicable, because you have to check the code word where the one is present, minimum one. So for the second code word, so their number of one is 3 4, so for this case this is 4. If you consider this one, that is this one, if you consider on there, so how many number of one is there, 1 2 3 4, so here also d mean is 4 on there. If you consider last one, if you consider, so how many number of one is there, total 8, so you have to write down 8 is the d mean on there. If you individually for the code word, if you write down the weight for that particular code, so which one will be the minimum, and that one will be defined as a 4, so d mean is the 4 on there. So by identifying the minimum weight for individual code, you can also able to identify what will be the d mean. And theorem position, already I told that kind of formation, that is the this one, um, this one 17 point what, no, 17.1, what is defined, the minimum distance of a linear block code is equal to the minimum weight of a non-zero code word vector. So here non-zero means each and every term for the code word is as a 0, so that one you should not consider on there. Okay, so by this way you can able to identify the value of d mean on there. for that particular question. Now question number is that find the error detecting and correcting capability. Error detecting will be, formula was d mean minus of 1. This is the error detecting. So d mean is 4. So 4 minus of 1, that means 3 number of bit position. If there any error is occurred, then at the receiver side it can able to identify, yes, there's some error is occurred. And how many number of error correction will be? So this is defined by 2. So 4 so the value will be 3 by of 2. So one number of bit position error can be correct. That means if there one bit error is occur, and that time it will be obviously detect with also it can be correct the position where the error is occur. Okay, so check that it is written on there also. So this LBC can detect up to d mean minus of 1, that is 4 minus 1, 3 bit error, and can correct up to 4 minus 1 by of 2, that means 1 bit error. Why this is 1 is written? Because already told you that you have to take the value of integer 1 only there, because 3 by 2 is result will be 1.5. So 0.5 you have to not consider. Now there another one example. So I think the compression will become on there after this example. For the following 6 comma of 3, that is n is given on there as a value of 6 and k is given on there as a value of 3. Okay, so here the generator matrix also given, and generator matrix is given as a form of systematic form. I think you can now able to identify, because first one is defined as a ik and k is there 3. So this is 3 cross 3. This is identity matrix for the left hand side for the matrix, and right hand side this one is indicate the parity matrix. This is 101 as a row form, then 011 as a 110 on there. The question is that for the first one, find all code vector. So this is so much easy now. You already know that you have to do the operation v is equal to u into of g. U is there for the 3 bit number of variation will be 2 to the power of 3. That means total number of u will be 8 types, and it will be starting from the 0002 up to 111, and G is already, this is systematic matrix, you have to apply on there and you have to do the multiplication. Look that there it is given to you. This is uh, U and G. This is the U is given on the total 8 number of variation, and G is already in the question it is given. So this is G is given as a this one, and then you have to got the value for the individual masses, what will be the code word. Okay, so from here you can able to identify what is the Hamming weight for the first one. For the each and every one is the 0, so you have to not consider the first one. Now second one, and there for this case here number of one is the 3, so here Hamming weight will be 3. For the third one also, that is this case, there also number of one is the 3, so you have to Hamming weight is 3. Now you consider this one, as I said this one. So how many number of one is there? Total number of 4. So Hamming weight is here 4. And the last one, this is 111 000. So value will become as a form of 3 on there. So individually you can got it the code word Hamming weight. So which one is the minimum on there? 3. So D mean is there 3 on there. Okay. Now if you design the encoder diagram or encoder circuit, because the question also given that draw the encoder circuit. To do this one you just follow the process. We already know that v is equal to u into g. So this is for the c is written for the code word, and this is let c0 c1 up to c5. Why this is c5? Their number of code word is 6, So if you starting from the 0, then last one will become as a suffix. For the C is 5, and number of bit for the message is there 3. So this is starting from the 0 up to D2. And why it is written as a MSB position, or this is the left hand side as a starting of 0? Why not it is starting from the 5, then 4, then 3, in such way at the position for the right one, as we write down for the binary case it is as a 0, because here ik is written first. Okay, here ik is written first, and there after that it is p. If you alter the position, then it will be also altered on there. So from here you can got the value for the C0. What will be the C0 value on that case? By using the multiplication, only row will be multiplied with the column. So here the C0 will be as a D0. For the C2 calculation, for the second one you have to multiply. So here at the second row only 1 is present, so it will be D2. Same way for the C2 is the D3, and for the C3, if you consider for the C3, what happened for the C3, what will be the value? This will be D0, D1, D2. So C3 means here um, D0 and D2 is present. Look that here, this is D0 and D2, but D1 is missing on there because this is 0 for the generator matrix. So the value for the C3 will be D0, D2. For the C4 if you consider, for the C4 you consider that time, which one is missing on there? Only missing is D0, so it will be D1 XOR of D2. If you consider for the C5, which one is missing on there? For the last one column, which one is missing on there? There D2 is missing, so the equation will become for the C5 will be D0 XOR of D1, D0 XOR of D1. Now there, this one is the uh, input or code, sorry, bit, input bit, that is defined the U, and they are formed as the D0, D1, D2. To get the value for the Z0, so C0 to get value, so it will be directly connect with the channel for the C0. If you consider for the C1, so that one also directly connect mm, with the D1, because the equation is given to you as such. This is D1, so D1 is directly connect with the C1. If you consider for the C2, that one is D2 is directly connect with the C2 channel. Now if you consider for the C3, so this is XOR between the D0 and D2. Look at D0 and D2 use on there to get the value of XOR. So this is C3. Now for the C4, C4 is D1 and D2. This is D1 and D2 is different. So this is D1 and this is D2. They are XOR operation to get the value of C4. And last one is that for the C5, this value is coming as a form of XOR for the D0 and D1. So this is D0 and D1 to get the value of C5. So this is the encoder circuit diagram. I think you can able to understand also. And we have to check the what is the another one question. Oh yes, for the last one, this is given that find the minimum Hamming weight. So this is so much easy. So minimum Hamming weight we already calculate from this uh, ultimate Hamming weight. So which one is the minimum weight on there? 3. So Hamming weight will be 3 on there. So you can able to identify Hamming weight from the table. This is the d min is equal to 3. So this is also extra thing is given to you, that is the parity generator matrix. And G is given as such, so it will be the transverse of the P parity matrix. Transverse form is 2 of I n identity matrix of n minus of k. So this can be um, generated from that particular question also. Now lastly, for the second day, we also define, or we also go through that particular question, that is the transmitted code word. It as I say, this one transmitted code word is this one. This is the 101011. That is the total 6-bit message. For the message of 101, look that for the message 101, for the message 101. So here for the message 101, the message will become 101011. So 10111, this one is written on there. But at the receiver side, due to the reason of noise or any another kind of reason, their received code word is come as such. Received code word is as such. So how can we detect or correct the code word? Okay. So still we explain the what is the code, what will be required before the transferring the message, and after transferring at the receiver side, how the detection will be processed and how the value will be altered to get the desired one. It will be discussed in the next class. Till I have to say bye and have a good day.